Hello, AB Calculus. It's Mr. Canfield. Today we look at chapter 29, Riemann sums. All right, so our book is kind of out of order in terms of a logical progression. If you want a slower exposition of all this stuff, I have a two-part video from a previous year. I start out talking about, it's the wrong chapter, but whatever. This is going to try to be an abbreviated video. So I know some of you guys listen to me at 1.5 speed or 1.25 speed, so I'm just going to try to make a slightly shorter version for those of you that pick up what I put down a little bit faster. So if you remember, we learned about integrals, and we learned that integrals are the area underneath a curve. And today we're going to just go through a little bit of the history of that. So there's this dude, Bernard Riemann, say Riemann, not Riemann. That way you sound like you know what you're talking about. So, so here's the way this works. Before we found the integral, or if we're unable to do an integral, we can do an approximation. So instead of knowing the exact area, we can say, hey, well, here's a rectangle and another rectangle, and these rectangles are, we set the base, so like, oh, I'll just, from here to here, I'll do two rectangles, and I'll do a base of 2 then, so that so they're evenly spaced. And the way that you find the height of the rectangle is you go to either the left side or the right side of the rectangle, and you find out the y value of the function. So, you know, whatever our function is, we go, oh, well, the y value here is, you know, looks like, I can't read. And then the y value here is that. So this is a 2 by whatever, and this is a 2 by whatever. Add those areas up, boom, you have an approximation for this area. And with 2 rectangles, it's bad. You know, we got all this leftovers. So if we went to 4 rectangles, you'll notice we have a lot less leftovers. And we just find the y values again at the right-hand side of these different rectangles. Or you could even go to a half, and you'll see that the more rectangles we use, the closer to this actual area we get. And the spoiler that we've already learned is that if you were to use an infinite number of rectangles, you would get the exact area. You can't use an infinite number of rectangles, but an integral lets us calculate what it would be if you could. So, so the function in the problem above is x squared plus 1. Let's estimate the area from 0 to 4 using 2, 4, and 8. So it looks like here are 2 different rectangles. We've got a base of 2, so I can say 2 plus 2. All right, so the height here, well, looks like we're plugging in the x value 2. If we plug in 2 there, it's gonna be 2 squared plus 1, so 4 plus 1 is 5. And then here, we're gonna plug in the x value 4, so 4 squared plus 1 is 17. So it's 10 plus 34, 44. If we move to 4 rectangles, what's the base of each of these rectangles? Well, it's 1, so I can say 1 times my first area, 1 time, wait, this is obnoxious. Don't do that. Say 1 times, so instead of doing 2 times each one individually, I could do 2 times the sum. Like I could pull the 2 out. We pull the base of the rectangle out front. And then I just need my 4 different heights. So my first height here, I'll plug in 1. So 1 squared plus 1 is 2. Then I'll plug in 2. So 4 plus 1 is 5. Oh, I already have 17 at the end as well. And then I just got to find that one, which is 3, 9, so 10. So 2 plus 5 plus 10 plus 17. So 27, 34. Is that right? 7, 24, yeah, 34. Okay, so 44 was our first approximate area, then we got 34 as an approximate area. And you'll notice each one's gonna be smaller than the previous one, right? I'm not bothering to do this one, but the base of each rectangle is 1/2, and sure, you can go in and use your calculator. I mean, well, you don't need to use your calculator. You should be able to do these without your calculator. Let me grab my calculator. Hey guys, welcome to my faster video. Let me go off into the other room really quick and grab my calculator. To get these fast, instead of having to plug them in each time, you just go to your, go plug them into y equals, and then, oh, these aren't going by the numbers that I want though, but you can do window set, it's a second window, and change independent to ask. Oops. And then you could do that. Or you could realize that we're starting at a half and going by a half. So I could do table set, change it to auto, start at a half, and we're going by a half, and then it populates it. It doesn't really matter, lots of options. But you'll find that area is even closer. And then, so let's talk about some things here. First thing, you don't have to draw it. I always do. Especially as a teacher, I always draw it because some people really benefit from the picture. The more rectangles you create, the more work you have to do. It's a lot of arithmetic and it's annoying. But the more rectangles you create, the closer it is to the real thing, or the smaller the error is. So if you have no error, you have the true area, which is the integral. So we have this example. Let's say we're trying to find the area from 1 to 5. You'll notice that from 1 to 5 is only 4 units, right? We do 5 minus 1, that's 4. That's how wide this is. So we've got, there's 4 different ways that we do this area approximation. The first one that we talked about on the previous page is called a right-hand Riemann sum, or a right Riemann sum. Why? Well, because for each rectangle here, we went up the right side of the rectangle to find the y value. The left Riemann sum, surprise, surprise, instead of going up the right side to find the y value, we go up the left side to find the y value. So all this looks like is, area is, we've got this uniform base and then these 4 different heights. So you factor at the base. And our height is always the y value. It's always f of whatever the x value it is. So this is kind of a helpful way to think about this one. If we're trying to find it, so this is 1, 2, 3, 4, 5. These are different x values. Notice if we're doing 4 rectangles, we don't use all 5 x values. We only use 4 x values. We use the left x values. We use 1, 2, 3, and 4. That finds us these 4 different y values times our base of 1. So our approximate area is 58. We are not going to be doing this stuff for n rectangles in general. This is a great thing for people who want to be math majors and stuff like that. It's a little bit of a deeper thing. We're not going to cover that. It's not on the AP exam. That's the reason. If it was on the AP exam, we would talk about it. We won't see these until the end of BC, these sigmas here, if you stick with me through BC, or if you're a junior who can stick with me through BC. So right Riemann sums. So those went up the left side. These go up the right side. So notice how on this one, instead of using f of 1, f of 2, f of 3, and f of 4, we're using f of 2, f of 3, f of 4, and f of 5. So usually what I'll do is, when I'm doing Riemann sums, they usually have you do left and right, like, just because they have you do exercises, right? So I'll make an XY table, and like for this one, since I'm doing 1, 2, 3, 4, and 5, and then I pull my different y values. I'm just going to steal these from here. So 15, 16, 15, 12, and 7. Oops, 12. What I'll do is, so the left-hand Riemann sum uses all but the last one, and the right-hand Riemann sum uses all but the first one. So 15, 16, 15, 12, and then 16, 15, 12, 7. So these are our left and right Riemann sums. one of these is called the upper sum and one of these is called the lower sum, and it all comes down to concavity. An upper sum is an overestimation. Which one of these is an overestimation? Please tell me you're saying this one is the overestimation because it's got extra stuff over the actual curve. Which one of these is the underestimation or under approximation? Look at that one, the lower. So this is where drawing can actually really help. So in general, a concave up function, your left Riemann sum is going to wind up being an under approximation, but for a concave down function, your left Riemann sum is, wait, the heck? Fine, all right, look. It depends on where you are, doesn't it? So sometimes the left part is over, sometimes the left part is under, sometimes the left part is under, sometimes the left part is over. Well, this is a waste of your time. Okay, so. Keep going. All right, so, oh, it's not about concavity, it's just about f prime. What am I thinking about concavity? I'm thinking about something else. Okay, so when a function's increasing, that's when, all right, okay, so you can read that. You have a brain. So he goes through a way to do it in the calculator. Not super important. They never give you ones that are long enough that you need to do that. So the other two sums that we learn about are the midpoint sum and the trapezoidal sum. So the midpoint sum, if you notice, the midpoint sum has sum over and sum under for each rectangle. So in some ways we could say like this empty space and this extra stuff here, they are likely going to do some amount of canceling out. Like I have some overestimation, some underestimation, some underestimation, some overestimation, under, over, under, over. And so it balances out a little bit better. Big deal with the midpoint Riemann sum is instead of taking 1, 2, 3, 4, or 5 like we did before and we picked half of them, now what we do is we pick the midpoint to find the y value for each of these. So I'm going to do 1.5, find the y value there, 2.5, find the y value there, 3.5, and that's what all this is. Find those y values. When you do that, so we get 27.5. So from before, our two options were 58 and 50. Wait, is this the same function? Wait, I feel like we're missing something. It's a crazy different number. This is, oh, that's not that number. Okay. So we had 58, we had 50. So this was our left L sum, we can call it, our R sum. This one, yeah, let's get the right numbers real quick. So 15.75, I'm guessing he like divided this by 2 or something. 15.75 plus 13.75 plus 9.75, 55. Yeah, so the midpoint sum, out of the three of these, the midpoint sum often is the most accurate. And then we have the trapezoidal sum. And if you look at that error on the trapezoidal sum, whew, that's looking pretty nice. It's pretty close to the real thing. So we talked about this briefly in one of the other chapters, but the area of one of these trapezoids, remember that even though we're used to seeing a trapezoid like this and like with a, an angled side there, it's still a trapezoid. So the two bases are the y value on the left and the y value on the right. And the way that we find the area of a trapezoid is it's the average of those two. So you add them up, divide by 2, then you multiply by the base. So I don't normally write it quite like this. I normally write 1/2 base 1 plus base 2 times height. I prefer to put height at the end. It's a convention for me personally. That's kind of how I think about it. But you can do whatever you want. Something to notice here. So in each trapezoid, and so I'm going to use this side, then I'm going to use that side. In my next trapezoid, I'm going to use this one, then the next one. In this trapezoid, I'm going to use this one, then the next one. And then this one, I'm going to use this one, and then the next one. Notice how we use the middle trapezoid, or the middle y values, we use them all twice. So that's, instead of saying this, where it's each of them separate, you can say, well, hey, it's the first one plus 2 times the second one, plus 2 times the third one, plus 2 times the fourth one, plus the last one. So the first and last get counted once, every other one gets counted twice. And that's kind of the general form for doing it. And we get an area of 54. So 58, 50, 55, 54. And we can calculate the real thing using an integral. So let me go do that real quick. Integral from 1 to 5 of x squared. No, that's not the function, sorry. I'm thinking of the previous function we were looking at. 4x plus 12 minus x squared dx. Actual answer is 54.6 repeating. So midpoint sum wound up being the closest out of all of them, but the trapezoidal sum, which we can call the t-sum, was really stinking close. So, yeah. This is all there is to Riemann sums in general. So we can do a bunch of like practice problems and stuff like that. But you know, we see approximate the area under sine of x using 5 left and right Riemann sums. So this is where we can just, yeah, it's just doing practice. Let's see, let's do some of these wordy problems. And again, if you want more detail on any of this, my other video series, I've got 2 videos on this where I do these problems a little bit slower. So a traffic light turns red and the driver stops the car in 5 seconds. Good job. It takes a long time. Over those 5 seconds, the speeds in feet per second are recorded. The graph to the right plots those points. Find the area under the curve using and it's not really a curve because it's line segments, but you get the idea. Using a trapezoidal rule with 5 trapezoids, interpret the answer and explain why this is an approximation. Okay, so if I want to use trapezoids here, I know my trapezoidal formula is 1/2. Well, what's my height? Each of these has a distance of 1, so we can say our height is 1, and if we want to do Stu's way, we can put the 1 here. I'm going to put the 1 at the end, but I mean, we're multiplying by 1, so who cares? My first trapezoid uses the left and the right, so that's going to be 88 and 60. Those are my 2 y values. My next one uses 1 and 2, so 60 and 40. So that's where I can say 2 times 60 plus 40. And then I'm going to use 40 and 25, so I can say 2 times 40. And so I'm going to, for all these ones, I'm going to say 2 times them. So 2 times 60, 2 times 40, 2 times 25, 2 times 10, and then a singular 0, and then times 1 at the end. I would set this up, don't show any more work, show your answer. Showing any more work is a chance for you to make a mistake. So I got 179. So if I'm wrong here, it's just proof that the second we move on to our next step, we are prone to error. So what does this mean? Well, so this is an accumulation of miles per hour, right? Or feet per second. This is an accumulation of feet per second. So we took those feet per second and we added them all up, we stacked them all up. This is gonna mean, take all those feet per second, add them up over those 5 seconds. This is how many feet we went. So it was 179 feet to stop. Why is this an approximation? So an integral of a function will give us the exact area. So it would give us the exact amount of feet to stop. This is taking specific discrete values and finding an approximate, like there's some real curve. He's not jumping from 88 miles or 88 feet per second to 60 feet per second. It's not a jump. There's some gradual stuff that happens, but we don't have that data, so we can't do that. You jump out of a plane. Good start. Before your parachute opens, you are in free fall. While your speed increases, your acceleration decreases as you fall because of air resistance. The table to the right gives the acceleration for the first 6 seconds. If time is measured on the x-axis and a is measured on the y-axis, find the area under the curve using a trapezoid rule of 6 trapezoid. So this, you can just do trapezoidal rule for this. Not as calculus-y as we want to get. So let's yeah, I think we're good. So, hope this was helpful. Again, if you need more, the other videos I think go through everything. So, or just get in touch with me. Have a good one. Bye.